In this video, we'll talk about trigonometric functions of angles. So in the last video, we talked about trigonometric ratios for acute angles, that is, angles defined specifically in a right triangle. So now we'll extend the definition of the trigonometric ratios to all angles. So we'll go through the trigonometric functions of angles, and then we'll go through evaluating trig functions at any angle. I've got like a process for you all to follow as we begin to work through these. So to start, let POQ be a right triangle with acute angle theta. So there's our theta. Place theta in standard position. So what we're going to do is we're just going to grab P and we're just going to drop it right there in standard position. So now we've got this angle theta and we can rotate this all the way around as many times as we like in one direction, or we could go in the opposite direction as many times as we would like. But it's important that we define it this way so we can open up the domain of our trig functions to all angles. So the definition of the trigonometric functions. Let theta be an angle in standard position, and let Pxy be a point on the terminal side. If r equals the square root of x squared plus y squared is the distance from the origin to Pxy, then sine theta equals y over r, cosine theta equals x over r, tangent theta equals y over x for x not equal to 0, cosecant theta equals r over y for y not equal to 0, secant theta equals r over x for x not equal to 0, cotangent theta equals x over y for y not equal to 0. I've drawn a couple figures down below so you can see a couple different versions of it. So if we start in standard position over here, we trace out our angle, and then we've got Pxy on the ray connecting the origin and that point. Interestingly, it does not matter where P is located on the ray connecting that the origin and that point. If we slide up along that radius, if we extend the radius out, we'll just be creating other similar triangles. So if I did that, for example, we have a similar triangle with the same angles. So think of the trigonometric functions being really defined in this case in terms of the angle, not so much the sides of a triangle. And then in the other one, I have another angle here going in the opposite direction, and another Pxy just to highlight that we've extended the domain of the angle to negative infinity and positive infinity. So lastly, to evaluate trig functions at any angle theta, we first have to identify the reference angle theta bar. Now this should make you think about t bar, the reference number t bar that we used in trigonometric functions as defined on the unit circle. And the reference angle theta bar is defined as, for any angle theta in standard position, the reference angle theta bar associated with theta is the acute angle formed by the terminal side of theta and the x-axis. So very similar idea, but now instead of looking at the shortest distance from the terminal point, we're looking at the smallest angle from the terminal side back to the x-axis. So that might look, for example, something like this is our axes, and we had that ray with this theta here. Theta bar would be that angle, the purple angle. And like t-bar, theta bar is supposed to remind us of quadrant 1 to make it easier to compute the trigonometric ratios for any angle theta. So once we've identified the reference angle theta bar, then we determine the sign of the trig function. And this just comes from noting the quadrant in which theta lies. Remember, in quadrant 1, we have a positive x and a positive y. In quadrant 2, we have a negative x and a positive y. Quadrant 3, negative x and a negative y. In quadrant 4, we have a positive x and a negative y. So this will just make it easier to identify when suppose we have a cosine. Remember, that's an x over the radius. it'll make it easier to say, okay, well, the radius is always positive, so if x is negative, then cosine is negative, right? And then lastly, we find the value of the trig function using theta bar in quadrant 1 to find the value and then applying the correct sign. So kind of to summarize, we find theta bar, which is supposed to remind us of the trigonometric ratios in the first quadrant, and then we look at the quadrant in which theta lies to find the SIGN sign of our trig function, then we combine that information. So now let's look at a quick example. Evaluate sine of 240 degrees. So this angle has its terminal side in quadrant 3 because 240 is greater than 180, which would be the x-axis, and 270, which would be the negative half of the y-axis. So that lands us like right here. That's 240 degrees. That's theta. So then this would be our theta bar, since that's the smallest angle between the terminal side and the x-axis. So theta bar is therefore 240 degrees minus 180 degrees, which equals 60 degrees. Since we're also in the third quadrant, this implies that sine is negative, since we have negative x and negative y, so we have negative y over positive radius. And we know that sine of 60 degrees equals the square root of 3 over 2 by our special rights, 60, our 30, 60, 90 triangle. We have a radius of 2, side opposite 30 of 1, side opposite of 60 root 3. So again, this definition is the y coordinate, the y value over the radius. So that gives us the square root of 3 over 2. And then, since we have a negative sine of our theta bar, which is 60, that means negative root 3 over 2 is sine of 240 degrees. So this is our answer. So once again, first we make sure we know where our angle is, our theta, then we find our theta bar, check to find the SIGN of our trigonometric function, find the value of the trigonometric function at theta bar, and then combine that value with the correct SIGN that we got from the quadrant in which theta lies.